Hi everyone, I'm here to present our work GeoEval benchmark for evaluating large language models and multimodal models of geometric problem solving. And this work is being done by with my co-authored from the Chinese Academy of Science and supervised by my supervisor Yashin Mushifaki. And this paper has been accepted as a full paper in ACL 2024 findings. First, I want to describe the motivations why we conduct this research. And recently, with the advance of large language models and multimodal performance on different tasks, and we want to understand how these large language models and multimodal performance on geometric problem solving. However, in the research area of geometric problem solving, we lack the standard uniform benchmark for evaluating these models. Previous data sets lack a standard format and there are not insufficient diversity in geometric shapes. Basically, only focus on the flat geometry without considering solid geometry and analytic geometry. And we call it monotonous problem types. As a result, we propose the GeoEval benchmark to evaluate the proficiency of the large language models and multimodals. In general, GeoEval consists of 4 subsets. The first one is Geo2000. It is sourced from the 7 public datasets sampled uniformly from them to try to cover a wide range of geometric shapes. Another one is GeoBackward. GeoBackward is designed to evaluate models' backward reasoning ability. Basically, we mask a condition from problem statement and append the answer to the problem statement and would like the models to given the answer of the problem and let the model the answer what the condition is. And also we have geo-augmentation data subset. We try not to change the statement of the problem, but instead we rephrase the problem statement by ChatGPT to provide more semantic diversity. And also we include a geo-hard subset. This is sourced from our own private copyright data set, including solid geometry and analytic geometry. All these subsets are proposed to try to prevent the scenario that large language models and multimodals may see these resources during the pre-training phase. As you can see from the left corner figure, you can see this is a distribution of where does the GeoEval 2000 is sampled from, and we try to allow for uniform distribution according to the data size of each subset of each data set. And on the right corner figure, you can see we can try to cover a wide range of geometric shapes in our benchmark, including the flat geometry and the solid geometry. And here is an example from our GeoEval hard subset. You can see we mainly focus on solid geometry on the left one and analytic geometry on the right one. We have provided a question and we have provided a diagram and also provided the choice and a golden answer. There are 5 features when we try to create this GeoEval benchmark. The first one, we want it has a feature of comprehensive variety, which means that we want the benchmark to cover a wide range of geometric shapes. And also we want to incorporate various problem types. So we want to not only focus on flat geometry, but also solid geometry, analytic geometry. And also we consider dual inputs of a benchmark. So some problems in our benchmark, they only contain with a solid problem statement, but some of them, they are accompanied with the diagrams and problem statement. This is designed to evaluate the different scenarios in large language models because they can only take input, text as input. And also we cover diverse challenges. We try to build a backward subset, augmented subset, and a solid subset to try to provide out of distribution data set to address the data leakage problems during these models pre-training stage. And also we try to create an algorithm to indicate the complexity level of each problem. And here's a comparison between our GeoEval dataset and our dataset. And previous method, they are usually they don't only focus on one certain geometric relationships and also only focus on flat geometric shape, and they are also they do not have diverse challenges, and they do not provide the complexity ratings. But our models, we are sampled from the 7 public data sets, and also we contain 3 additional data sets: backward, augmented, and hard. And also we cover 5 solid analytic geometry, and also our inputs are both text and diagram. And we have incorporated diverse challenges, and we have annotated all the complexities of each problem. We meticulously select these models as the evaluation models. The first one, it will select large language model specific in programming code with coding, and also since we're focused on the geometric problem and they are belong to mathematical problem scenario, we try to select visual math, which is pre-trained on math corpus. And also we have selected commercial models like GPT-3.5 and GPT-4. And for the models, we try to, this nowadays multimodal models, they are given a vision transformer architecture as a vision encoder. We try to select them according to the decoder. They are using like Lava, they are based on Visuna. Channel-VL is using Channel as decoder. MPlug is using Llama as a decoder. Instruct Blame is using Visuna as decoder, and GPT-4V. All the models are evaluated through the zero-shot approach, utilize the straightforward instruction prompt to directly guide them to generate the reasoning process to solve the problem. And since different models, you try to generate the reasoning process in a different way. As a result, we try to extract the answer by GPT-4 and also use the pattern match for post-processing. And we treat extract answer as correct if it matches a golden answer. Here is an example about the prompt we used to get a GPT-4 to extract the answer from the model output. And in the first example, we try to extract that the extract answer is A, and we just compare the extract answer option letter A with a golden letter. And first, we compare language models performance of our GeoEval benchmark. We can see that the reason math featured on mathematical corpus outperforms all the other models on 3 subsets. However, it performs much worse on GeoEval hard data set, which is sourced from our own data set. And also we compare the multimodal models on our GeoEval benchmark. We can see that our model GPT-4V outperforms, and MPlug outperforms other models with a large margin. And basically, the best model of the large language model are VisiMath. The best model perform with the best performance of multimodal models of MPlug and GPT-4V. And if we compare between best large language models and multi-models, we can see that VisiMath outperform the MPlug on the GeoEval 2000 subset. However, it's achieved slightly worse on GeoEval backward subset. And also, the VisiMath 7 billions version 1.1 outperform MPlug on augmented dataset, but the original version performs slightly worse than the MPlug. Worth mentioning is that the VisiMath model, despite it perform very good on the GeoEval backward, GeoEval augment, their performance on the hard data side, which is collected from our own data set, which we assume that this large language model shouldn't pre-seen this data during a preaching stage. VisiMath perform very bad on the hard data subset. And here's the important findings from our evaluation. The first is pre-train on a mathematical corpus is crucial, but it may not be enough. This is demonstrated by the model performance of VisiMath. VisiMath performs very good on Geo 2000 backward or segmented subset. However, it performs very bad on GeoEval hard subset. And also, we also have very interesting finding that GPT-series model benefit from their use in the rephrasing geometric problem state. We can see that both GPT model, their performance get enhanced on the GeoAugmented subset compared with their performance on GeoEval 2000. Remember, GeoEval subset is rephrased from the GeoEval 2000 by ChatGPT and without changing the problem statement. As a result, they are actually asked the same questions. However, we can see that the model performance got improved a lot if the problem statement got rephrased by ChatGPT. And also we can see the multimodal models unplugged, it maintains relatively stable accuracy across all subsets. We also show results across different subjects. We can see the WizardMax expert on the purple line, report that WizardMax 7 billion is expert on flat geometry, and GPT-4v looks the yellow one is better than solid geometry like cubit, cube, cylinder, prism, sphere, and cone. Also, we are interested in that if we can provide these models with additional geometric diagram description as a text input, whether it will help the models solve the problems. We can see that GPT-4v and WizardMax 7 billion, their performance all get improved if they are getting additional geometric diagram descriptions. This scenario is more evident if we provide additional input for WizardMax 7 billion, because large language models, they cannot read the diagram directly. And also we have test external knowledge required. So we try to, because in order to solve some geometric problem, you have to use some external knowledge, such as the volume of pi. This won't be provided in the problem statement. And we have in the bottom table, a figure we have shown that the orange bar is the model performance without using external knowledge. The blue bar is the model performance on the problem statement have to use the external knowledge. Because all the model performance, except for WizardMax, they got declined if they have to solve the problem using the external knowledge. However, we can see for WizardMax model, its performance is quite similar on the problem statement required using the external knowledge and the problem statement without using the external knowledge. This is reasonable because WizardMax model is pre-trained on mathematical corpus. It should contain more external knowledge regarding the mathematical domain compared to other models pre-trained on generated corpus. We have also reported model performance according to different problem lengths and variable complexity. You can see that this figure shows that model performance according to different problem lengths. You see all the models' performance declined when the problem length increased. This is reasonable because as the problem length increase, it means the problem statement is more harder. And we also show the model's performance according to different complexity levels of each problems. We can see model performance also got declined if the complexity of the problem increase. And thank you for listening to my presentation of our ACL 2024 exam papers. And this work is done in our new research laboratory. And you can ask me questions if you have any by sending an email to this address. And also please do follow the Twitter handle of myself and of our new research lab.